Express the volume of the solid inside the sphere, x squared plus y squared plus z squared equals 16, and outside the cylinder, x squared plus y squared equals 4, as a triple integral in cylindrical coordinates and in spherical coordinates, respectively. So all we have to do here is express the volume of the solid inside the sphere and outside the cylinder. So we just have to write the integrals for this. We don't actually have to compute them. So let's take a look at the picture. Here's the picture we're looking at here. And remember, we're outside of the cylinder, but inside the sphere. So what we're looking at here is really this bead. And that's gone. So we're going to find all of that other stuff. So that's what we're dealing with. So we're looking with a sphere with a hole drilled through the center of it, of radius 2. So that's exactly what we're looking at here. So we just have to set that up in terms of cylindrical coordinates. So here's the cylindrical transformation. Now, one thing I'm not going to do in this video is I'm not going to go through the Jacobian again. I know my Jacobian for cylindrical is R. And that would be R theta Z, and that equals R. So when we look at the formula for cylindrical, this is what it is. So we have our R here, and since we're talking about a volume again, our FRZ, theta Z here is going to equal 1. So that means we're going to have the triple integral, and then we're going to have that 1 there, and then R dr d theta dz. And again, I'm not sure in what order I want to put my R, theta, and z yet. I may want to put the dz first again. And as we play around with these equations, we'll figure out which one goes best first. So for this one, I'm going to do my dz first. So then notice for my z, I'm going all the way down to there and all the way up to the top of that sphere. So that sphere is going to be my upper and lower bound for z. And I have z squared equals 16 minus x squared minus y squared. Now again, I have to have it in terms of r. So one thing I noticed here was this is really 16 minus x squared plus y squared. And x squared plus y squared equals r squared. So then really for z squared, I get 16 minus r squared. And then to find z, I would square root both sides. So it's going to be plus or minus the square root of 16 minus r squared. Now think about it this way. If I just take the positive, then that's going to be the upper half of the sphere. And then if I take the negative, that's going to be the lower half of the sphere. So that means I'm going to have, so below would be negative square root of 16 minus r squared, and the upper bound would be positive 16 minus r squared. Now for r runs from, now remember the center here is gone. We don't have any of that there. So that's out of there. And if you think about r then, I would have to look at this equation here, which gives me r squared equals 4, which tells me r equals 2. So r is going to run, and that's going to be the inside of that volume. So that's going to be my lower bounds, because that's the smallest it can be. So if I'm thinking about r coming out of the center here, it can't come out here in that piece. But after that piece, it can. So it's going to be in there. So it's going to start at 2 and actually go out 2. And if you think about what this sphere is, that's going to be where my r is going to be 4. Because if my z is 0 now, I really have x squared plus y squared equals 16, which tells me my r is then going to be 4. So this is going to be from 2 to 4. And then my theta, think about what theta does. I come out on the x, and I go up with the z and down with the z, so it's going to be this piece here. And then I got to take it all the way around. So that means my theta then is going to be 2 pi. So 0 to 2 pi. So there's the triple integral that we would have for cylindrical coordinates. Now we're going to do spherical coordinates. Now as for spherical coordinates, that's going to be a little different here because we need the spherical transformation, which is here. And we also need the formula for spherical coordinates, and that's what I want to show you now. And here's the formula for spherical. So if you look at this, my f rho theta phi is going to be 1 because we're talking about a volume here. And notice this rho squared sine phi. In my last video, we realized that that's the Jacobian for this triple integral when I go to spherical coordinates. So I did calculate that in the last video. So if you want to see that, go back. So anyways, now we're going to set up the triple integral for rho theta phi. So now if we look at our rho here, we can see that x squared plus y squared plus z squared equals rho squared. And that's going to take care of this equation here, x squared plus y squared plus z squared equals 16. Now think about rho here. Now it starts from the center. And if I think about my rho coming out, that's my three-dimensional radius, so it's coming out this way. And also keep in mind here, too, that my phi runs downward all the way to pi if necessary, which is at the bottom. So that rho is going to come out, phi is going to drop it all the way down, which is going to create this slice here. And then theta is going to take it all the way around. So theta always follows the same rule in cylindrical and spherical both. But what we're going to do here is we have this phi to consider now and this rho. And that rho, like I said, is the three-dimensional radius. So now then, if I'm thinking about rho comes out here, but it doesn't start until after this value here. So this is going to be the lower bound for rho, and this here is going to be the upper bound for rho. So right away we can see that x squared plus y squared plus z squared equals rho squared, which tells me this right here equals 16. So that means this equals 16, which tells me rho squared equals 16, which tells me rho equals 4. And that's going to be the upper bound, remember that. So that means right here in this formula here that that's going to be 4 up there. So now we need to figure out that lower bound, what's going to give me this here. So what that means is we're just going to plug in for that. And that's how that works. So we're going to have x, and we're going to use this equation for that because that's the cylinder then. And we're going to be after that. That's going to be that lower bound. So my x is rho sine phi cos theta squared plus rho sine phi sine theta squared. And then that's going to equal 4. And then we're just going to work this out. So I'm going to square both of those. So that's going to be rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals 4. So now from here, we can factor out a rho squared sine squared phi from both of these. And that's going to be rho squared sine phi, and what we have left is cosine squared theta plus sine squared theta, and that's going to equal 4. And notice this, that this here equals 1. So now that's going to result in rho squared sine squared phi equals 4. And then if I'm solving for rho here, because I need the lower bound for rho, I'm going to move over the sine squared of phi. So I'm going to divide by that. So I get rho squared equals 4 over sine squared phi. And then I'm going to square root both sides. So then my final answer for rho then is going to be rho is going to equal 2 over sine of phi, which I can also write as 2 cosecant phi. So that's what my lower bound is going to be for my rho. My rho is going to actually be 2 secant phi. So that's that piece there. Now we're going to have to figure out phi here, because phi is next on the list. So now phi is going to be a little interesting here, because remember, we're starting from the center here, and we generally start from the upper or positive z axis. But notice this, there's nothing there. It doesn't really start until that value there, which is actually my x squared plus y squared equals 4. So I have to figure out what that angle is, because this angle here is the angle where I'm going to actually start my phi. So phi doesn't live in here at all. It lives after that. So I need to figure out what this angle is. But also keep in mind, even though it starts past this, that's also where this intersects with it. So it's where these two intersect is where, we are going to find phi. So essentially what I'm going to do is I'm just going to sub one into the other for those two. So notice x squared plus y squared equals 4. So I'm going to plug that in where I see x squared and y squared here. I'm going to put 4 there. So that's going to be 4 plus z squared equals 16. So essentially I'm just subbing for those. I'm going to move the 4 over now. So that z squared equals 12. And then when I square root both sides, z is going to equal 2 square root of 3. And then what we do here then is, notice for this bottom piece here, z equals rho cos phi. Now rho, think about rho here. If I'm meeting at this point here, my rho is actually going to be 4, because that comes from this equation here. Anything out to the boundary there is going to be 4 for rho. So that means my rho is 4. So if I'm going to use this piece right here for my z, this is going to equal 4 cos phi. So we get this. And then to solve for phi here, I have to move the 4 over. So cosine of phi equals 2 square root of 3 over 4, which is really just square root of 3 over 2, which this is one of my special triangles. I don't know if you know that or not, or if you remember. Cosine is adjacent over hypotenuse. And there's my right triangle. That means this is going to be a 1 over on this side. So this angle phi then is going to be pi sixth. So my phi is pi sixth. And that's where I start. So I'm starting at this pi sixth here. And I'm going to run all the way down. Now keep in mind here, I'm going to have some symmetry here. So this down here at the bottom is also going to be pi over 6. So that means in here, it's going to go 5 pi sixth. Because altogether, if I go from the top to the bottom, it's going to be 6 pi sixth. So I'm going to take away this pi sixth and this pi sixth. So that's going to be 4 pi sixth for this piece here, but I got to start with the pi sixth here. So I'm going to go from pi sixth to 5 pi sixth because I'm going to be 1 pi sixth short. So for phi then, That's going to be from pi sixth to 5 pi sixths. And I'm going to have to spread this out a little more. This looks horrible up there, so I'm going to fix it. And then the last one for theta, that's going to be the easy one, because remember, I got all of this piece here. And how am I going to run that? I'm going to run it all the way around. So that's going to be from 0 to 2 pi. So there's the integral. Now if I run it in cylindrical coordinates here, or I run the integral using the spherical, I will get the same answer for both. Now the problem here only stated express the volume. It didn't say find the volume. So this is an expression and the spherical coordinates is down here. So there's our two answers.